Recording.
Okay.
Okay. All right. So this is presentation on the effects of canary grass on dissolved oxygen. And we're looking at Chimacum Creek. And I don't know if you ever thought about it, but canary grass is something like an iceberg. Did you ever think about that? Probably not. But just looking at what that excavator is holding up, the green stuff on the top, the grass, is pretty small compared to the whole thing. All of that brown are rhizomes, and it's massive, just keeps growing. So that is what causes some of the problems, besides the leaves. So we're looking at Chimacum Creek, looking downstream from the bridge at what I will call the port property, which used to be the Short family farm. And this is 1 year after it was cleared. And you can see that along the right bank, the edge of the bank is probably over here, and the canary grass is extending out. There must have been maybe the canary grass that was excavated the year before sitting along here. That's why it's dead brown. And you don't have much coming out from this bank because of that, I think. So that's 1 year after the clearing. And this is what it looks like 2 years after. And you see it coming out from both banks now, even some little islands in the middle forming. And this is 3 years after, just bank to bank. And this was 2023, which is a lot of the data we'll be looking at happened in 2023. Temperature has a big effect on dissolved oxygen. Colder water can hold more oxygen. And just to give you an example, at 27 degrees Celsius, saturation occurs at 8, sometimes I'm going to say milligrams per liter. You might hear me saying parts per million. It's the same thing. 27 degrees, 8 parts per million, 16 degrees, 9.9, almost 2 parts per million more. So that's a big effect. And we know Chimacum Creek does warm up. And this is some examples of how it's been warming up since I started collecting temperature data on temperature loggers, which record every hour in 1998. The bottom two lines that you see, the purple and the red, are taken at the upstream control stations on both Chimacum and East Chimacum Creek. They're in forested areas, so it's constant since 1998 and up to 2021. So we're looking at slightly increasing temperature trends. The green line is at the downstream station on Chimacum Creek. It's just above the estuary, and that is increasing. Now, part of the reason for this is that air temperature is increasing. And the upper blue line is taken at in Chimacum at a weather station. Now I need to define what we're looking at when I'm talking about temperature. We're talking about something very specific. We're just looking at the months of July and August, and we're looking at the highest temperature on each one of those days. So 62 days altogether. The highs for each of those days, taking the average of those 62 highs, that's what each dot represents. So anyway, if air temperature is increasing, naturally water temperature is going to be increasing just based on that alone. And this summarizes 29 stations in the Chimacum watershed, including tributaries, 83% of them had upward trends and 17% of them had downward trends. This is an example of one station. This was at Finn River. That's a forested area now. We did a CREP project on it, or actually two separate ones, projects that were done on it quite a few years ago. But this is data from 2021. It's shaded now. And, you look at that graph there, and you got highs all the way up around 28. The yellow circles are averages of 7 days, the daily highs for 7 days. Like you might say 3 days before, 3 days after, and that's the average. The blue lines are the instantaneous. I say instantaneous every hour. They're going up and down just because of nighttime and daytime temperatures are changing. But anyway, it shows you that there's some warm water in Chimacum Creek. This graph is of oxygen levels taken from the crack of dawn at about 5:30 on up to mid-afternoon at about 3:30. And you've got two different time periods there, last year in 23 and also in 2001. Now, I'd say what is typical when we're looking at it throughout the day, starting at dawn, dissolved oxygen is always lowest right at dawn because you don't have any photosynthesis going on during the night. So you kind of starting fresh at dawn. And as the sun comes up and shines on the plants in the creek and photosynthesis kicks in, oxygen goes up. And that's just exactly what you see for both Chimacum Creek and East Chimacum Creek in 2001. But looking at the bottom two lines, they're just flatlined. So what's going on there in 2023? And you notice those flat lines are low, below 3 parts per million, which is like what EPA calls the acute toxicity level. Anything below that, dead fish. When I say fish, we're talking about salmonids, trout and salmon. So the reason for that is right here. It's canary grass. And canary grass, it's got photosynthesis going on, but where is the oxygen going? Well, the grass is above the water surface. It's going just up into the air. It's not contributing anything to the water. Yeah. And more than that, it's shading out potential submerged vegetation. Now, in the foreground, you'll see some stringy green leaves. That's pondweed, which is common in Chimacum Creek. And, anything below the water surface, if photosynthesis is going on and it's contributing dissolved oxygen to the water. Another common plant is Elodea, where you have open water. You generally have quite a bit of Elodea. This is not Chimacum Creek. This is just taken from the internet to show you what it looks like. But let me say something else too. You also have respiration going on, which goes on 24 hours a day to plants, live plants in the water. And that's respiration is taking oxygen out of the water. Another thing that's happening here with all of that vegetation, it's all going to die, and you're going to have decomposition going on, and that's taking oxygen out of the water. And another factor where you have low gradient, which is much of Chimacum Creek, you don't have riffles. Riffles in a normal stream where you have pool, riffle, that's where your oxygen is getting into the water. In the case of Chimacum Creek, it's just getting in where you don't have riffles. It's just getting in from the surface layer. And I'm not sure how much that canary grass, just because you have a bed of it on the surface, even prevents oxygen from getting in there. So you have a lot of things against dissolved oxygen, and that's why we're seeing such low dissolved oxygen levels in the canary grass areas. Okay, so now we're looking at readings that were taken in one day in September last year. We're starting on the right in the upstream area that's wooded. This is up at Eagle Mountain Road, Jody Holt's farm. It's actually in the forest. You have lots of forest above it. So it's a control station. And we have oxygen 10.4. And then as we go downstream, all the way downstream at the very extreme left is that station. That's the upper end of the estuary. Well, we go downstream and we hit a low at station 3.9. Now that's river mile 3.9 up from the mouth. 1.1. That is at Red Dog Farm. There's a bridge there. The other side of the bridge is Woodbridge Farm. And that's like where you get the lowest readings. And then you're coming back up again after that, and all the way up to 10 parts per million at the very lowest station. So the red lines here are standards. The very top one here, ecology standard, they set dissolved oxygen at 10 parts per million. So you want to be above that. And I will say they do factor in, if you do have problems with temperature, they take it 95% of the level of the saturation level based on the water temperature. So there is a little standard there. But to hit 10 parts per million, you would have to have at 16 degrees, which is their standard for temperature, that's what you would need to hit 10 parts per million if well, I'm losing my thoughts here. I'm getting too complicated into this. Let's just say 10 parts per million. So EPA also has a publication, and they have said that anything below 8 parts per million, you're going to impair production. And production for salmonids, it's basically weight per unit area, but you could just think of it as fish size. And it's a sliding scale. You know, it's not like a magical everything is good above 8 and you get a 10 below it, then it's bad. It's just like the farther you go in dissolved oxygen, lower and lower, production is getting worse and worse. And if you think about it, survival for these juvenile coho in Chimacum Creek, length and size is the faster you can get bigger, the less things there are to eat you. So yeah, it just goes, it's worse the lower you get in dissolved oxygen. You want to grow as fast as you can. If you get all the way down to 3, EPA says below 3, that's the acute mortality level. And any salmonids that's in water below 3 for any length of time, they're going to end up dead. So this is where the data you just looked at was taken at this station, 3.9, Red Dog Farm, I'll call it. This is looking upstream from that station. So you don't see any water visible there. You see lots of canary grass there. There's even some cattails there, and just full of vegetation. This is at the port bridge looking downstream toward that station 3.9. So again, you just got lots of canary grass upstream from that station, and that's why dissolved oxygen is so low there. And this is East Chimacum Creek. Again, on the right, that's upstream control. That's in a wooded area. We got good DO up there. And it goes all the way, it starts going down from there to an extreme low at river mile 2.8. And what's at river mile 2.8? Well, we just call it Ovenel, the landowner there. And this is at the station, which would be about here. This was a CREP project done years ago. So you got lots of vegetation along here on both sides of this. And what you also have, this is another factor. Of course, we're doing anything on Chimacum Creek, and that's the beaver. And the beaver like to get in there. That's the bad thing about, planting trees are good, or shading it, and large woody debris and all of that. But they also make it very susceptible for beaver damming it up. And of course, this is a floodplain, and it doesn't take much to cause the water to come out here. And that's exactly what's happening. So the dams cause the water flow to come out into the canary grass. And by the way, of course, we all know that Chimacum Creek is channelized, and it's not necessarily the channel just happened to be in the lowest part of the land all the way down there. And when it comes out, it's just going to take the easiest path to travel and go through the canary grass. And then it goes across the road. This is one place here you can see, but there are, when you walk it, you can see other places where it's just coming out of the canary grass. I took the data right where the culvert is. The culvert up here had blocked up completely, water running across the top of the road, right there above the culvert. That's where I took my samples, and extremely low there. This is an aerial view. So the blue line is basically the channel. You got the vegetation on both sides in the CREP project. And then you have the canary grass that the water's just running through. We're going to look at a couple canary grass removal projects. This one was done in 2006, a half-a-mile reach, 7.5 to 8.0. That's just downstream of Eggenai Road. And the project started on August 15th, and it ended on August 24th. I started monitoring the data, and I always got there at the same time each day, about 11:30, just to counteract any photosynthesis might be changing it. We have 3 days with, we could call it baseline data before the project started, about 6.2 parts per million. The day of the project, it dropped down to 5.8. It's likely that was caused by biological oxygen demand by any sediment that came up into the water column. But after that, it starts coming up. We did have another low reading on the 23rd, again, probably because of the sediment kicked up having an effect. But after the project ended, you have readings 8, 7.8, 8.3, 8.8. So overall, after the canary grass was removed, you go in from about 6.2 on up to about 8. So that improved things. This is looking at another removal project done in 2010. And in this case, I have 7 stations that I was monitoring that bracket the removal area, which was river mile 3.4 to 6.2. I have a few stations, 3 stations below 3.4, and then 6.2 is at the very upper end of the project. So that station is just seeing water coming from above the project. The project started on July 15th. So we have one day, July 14th, the dotted line here. Consider that baseline before any work was done. So that's what the DO readings look like, starting up here and, going down at these low stations, 3.9 again, red dog. And 3.4 is at the bridge at SR 19, kind of where the Chimacum school is. Those are the two worst stations. So before the project even started, you're at about 3.5 parts per million. Not that great. They're pretty poor. But once the project started, the next day, you are down to 0.25 parts per million. You're almost down to zero. And the water there, when I was monitoring, and this is right underneath that bridge, SR 19, the water was black. And that black came, from the work that's done with an excavator. It's not dredging the creek. It's removing the canary grass. And the excavator is fitted with a rake just to pick up the canary grass and the rhizomes attached to it and removing it from the creek. But when you do that, naturally, you're going to disturb some sediment. And that's why the water was black. And that's from that BOD. You're taking the oxygen out of the water from that. And that's why it hit that extreme low. And at the time I was there taking the sample, there were 4 dead salmonids there. There were about 20 that were in distress. When I did go downstream to the next station downstream, I did not see any dead fish. When I first got there, the water was clear. I went back a little later and the water there was black, but I did not see any dead fish. The level down there was this point up here, above 4. So it was mainly the worst place was right at that bridge. Okay, so that was the day of the first day that work began. The next day, you're up here on the 16th, so the DO had come up almost to 3. And then on the 19th, you're up above 4. And then a week later, on the 26th, you're up above 6. On the 29th, you're up above 7. So after that period of time, your DO came up. You can look at the 29th compared to when we started. That's basically 2 weeks later. So conditions, after the immediate negative effects, the DO did come up, come up quite a bit. We're going to talk about some fish trap data now, fish data. This is Elisa Meany. She used to be an intern for the district, and she's married and got 2 boys now. This was a while ago. But the picture is to show you what a fish trap, if some of you haven't seen it, this is what it looks like. It's got 1/4-inch mesh, got a funnel on each end, baited with bread, and it's kind of easy for a fish to swim in and hit that hole and get inside. But once it's inside there, it's a little trickier to get back out. You got to hit the hole dead on, and most of them don't. So that's how we collect the fish. We just identify them, count them. They're never handled. They're just put in jars to identify them and released back into the creek. So this is at Red Dog Farm Bridge, where I conducted a bioassay. And I wanted to just see for myself, is this, these readings, some of you look at numbers, is it really as bad as what the numbers make it look to be? Am I getting good data? Those fish should be dead there. So I decided to do a bioassay. And I collected fish up at the Port Property Bridge. And I put them in 2 traps. I want to make sure they weren't crowded and, die just because there's too many fish in a trap. They were really spread out, so there's no problem there. There was definitely current flow in that little clear area there. The bridge provided some shade, so right underneath the bridge, it didn't have much canary grass. And I put them in that clear area there where I could see a good current going through there. And these are the results of the bioassay. But first of all, where the fish were collected here at the port property, the DO there, not high, but it was above 3, 4.1 to 5.4, two times that I measured it. I put the traps in on the 12th of September. This is last year, 2023, and left them overnight, pulled them on the 14th. That's why I have two different readings here for both of those days. And then immediately put them in a container, and it was just, a 10-minute ride to put them in at the Red Dog Farm, where the readings there on the 2 different days, the day I put them in, the day I took the traps out, 1.6, 2.2, acute mortality levels for sure. And when I pulled the fish, they were in there in the water 20 hours. So I had the one pumpkin seed, it was still alive. Sculpin was still alive. One cutthroat trout was dead, and 5 of the 7 sticklebacks were dead. I suspect that if I kept them in there longer, probably all of those fish would be dead. But I also suspect that if they weren't in the trap, fish, they're trying to survive. And a lot of times when things are not looking good, you see fish in distress right up at the surface, because that's where the oxygen is going to be the best, right near the surface. And when you're in a trap and you can't move to the surface, well, you just got to take what's there. Anyway, that's the bioassay. What we're looking at here is a comparison of 2 reaches. Finn River, where it's wooded. We did the CREP project. It's got shade everywhere along there. And down below, we're comparing it to the port property reach. You've seen some of the pictures there, just bank to bank canary grass. And we're looking at data that's collected from 2015 to 2023. And I want to acknowledge my best fish trapper, Howard Tees. He's a fish biologist on work in Alaska. He's living here, retired. And he is very consistent. He goes out there like every week, 4 quarters of the year. He's just out there, puts the traps in and gets the data. And he's been doing that since 2015. And that's 9 years of data. He's working on his 10th year this year. And he just had a shoulder operation. And I hope he recovers okay and he's able to go back to doing what he likes to do. Now, I just want to say that you look at this and this is looking at Finn River, you see months that are up and down. It's really not fair to do a month-to-month comparison like that, because you have fish hatching out of the gravel. In some cases, they're growing. When they first come out, they'll go right through the mesh of that trap. Then they're getting bigger. They'll stay in. Have smolts heading out, leaving the whole area, going out into the ocean. So you can't really compare across this way. But what you can do, and that's the purpose of this graph, is to compare what's happening in each month in the Finn River reach to the port property reach. The Finn River, a nice wooded stream, no canary grass. In the port property, well, you know what that looks like, solid canary grass in 2023. So just a casual glance at this, you can see that, in every one of these months, you've got more abundance, which is based on the average number of fish caught per trap setting. It's every month you've got more in the Finn River than in the port property. Same thing again, only with trout. And those trout, just making it simple, there's both steelhead or rainbow trout as well as cutthroat trout in the creek. Sometimes they're not the easiest to distinguish, especially the smaller they are. So it just makes it simpler just to call it trout. But anyway, they're salmonids, a lot like the coho, you know, the conditions, the DO temperature is similar. So again, you can see here that by and large, they're doing better in the Fin River stretch. This graph here, I have boiled everything down to one average reading of the number of fish caught per trap for the 9 years, 2015 to 23, for all of the months, get one average. And looking at the coho, you're at average at 0.3 fish per trap compared to about 0.1 at the port property, Canary Grass Reach. So, you know, you got about 3 times the abundance, I would say, in the Fin River Reach than the coho Reach. Now, if you think about 1/10 of a fish per trap setting, you can also think of it, well, it takes 10 trap settings to get 1 fish. That's the same thing. Trout, you got about twice as many in the Fin River stretch as the port stretch. And then things turn around when we're looking at pumpkin seed. Pumpkin seed, they're not supposed to be in there. And they're not what I would say native to our streams around here. They were put in a pond, and the overflow from that pond goes into Chimacum Creek, and that's why they're there. They shouldn't be, you know. Any fish is going to be competing, all those sticklebacks, which there's tons of those. I didn't put them on the graph, but it would go off the charts here. That's why I didn't have them on there. There's tons of them, mostly in the Canary Grass stretch, but you do have some up at Fin River. Anyway, pumpkin seed, you have more at the port stretch. Same with crayfish, and same with sculpin. So, opening it up for questions. Anybody have any questions about it? Well, since you don't have any questions, I'll show you 3 more graphs, okay? I thought you might be interested just to see how the returns are doing on Chimacum Creek. I got this from Randy Cooper with Fish and Wildlife from 98 to 2020. And, you know, just glancing at this, it looks like you had higher returns in the earlier part of these years and in the latter part. We don't have the last 3 years, 21, 22, 23. And the return in 22, I'm thinking we'll get I'm interested to see how high that bar is, because I know we had just based on hearsay and all, there were coho all the way up to Gibbs Lake, where they went up Naylor's Creek. So it seemed like 22 was a good year, but don't have that data to look at yet. This is looking at coho juveniles from 98 to 2024, 2 months in 24. And again, you know, it looks like things did better earlier on than more recently. One final graph, just to keep you aware that, you know, the fish's life cycle, a salmon spends more time in the ocean than it does in the creek. And we're focused on the habitat in the creek. There's not that much we can do out in the ocean, except in the big picture of climate change and all of that. So National Marine Fisheries Service, they provide this data, trends, It starts in 98, and it went right up to, I can't even read it on my, I think it went up to 22 or 23. I have pictures of you all on top of that part. So anyway, they're looking at different parameters, which they end up averaging. Each one of these little squares, they assign a number to, and they end up taking an average, and that's what you see in the gray bar, all these numbers. Then they convert it back into the colors, and they call this a stoplight trend, you know, red, yellow, green. Green being good, and yellow being fair, and red being poor. And the parameters that they look at, there's the whole bunch of them. Here's the whole line of parameters here. You know, the whole column is, each one of these is a parameter, and then they come up with a final average down at the bottom. But they're looking at temperatures, both surface temperatures at 20-meter temperatures, deep temperatures. They're looking at copepods, the number of them at different times of the year. They're even comparing what they call north copepods and south copepods. You know, not all copepods are alike, just like people. Some are fatter than others, you know. Even little copepods have fat. And it's the fat ones that the salmon do better on, they grow better on. So that makes a difference. And they're also looking at the juvenile catch of Chinook salmon and coho salmon. So they boil it all down, and they come up with a rank, you know. They turn it into a color just to make it easy for us to see. And I guess the main takeaway here is just to realize that, yeah, it's not all, you could do the very best you can for the stream habitat. But if things aren't doing well out in the ocean, you're not going to have a good return. And you can just look at this and see how variable it is. And, you know, the first date they have is 98. And I'm just thinking of, you know, some of those other, like the coho return for Chimacum Creek that Fish and Wildlife provides, you know, that seem to be better in the earlier days. I'm looking at 4 greens here. Of course, they're followed by 3 reds, and you get a bunch of reds here. And anyway, it's variable. So I'll stop now and say that's the end.
Thanks, Glenn.
Yep.
Always interesting. I just want to give folks a heads up. It looks like my Zoom account only wants this meeting to be 80 minutes. So that's for Joe. Joe, you'll be giving a presentation on the Chimacum project. So just a heads up that the meeting's probably going to end at 11:20, maybe. See what Zoom decides.
Yeah, well, thank you, Glenn, for the presentation. Your slide deck has been in my inbox for a while, for just like a few days. Eric Kingfisher had forwarded it to our staff, and I hadn't gotten a chance to look through it. So I'm really glad to just have the chance to have you kind of talk through each of it and understand it more. So that's really interesting to get to know the watershed more. Thank you.
Yeah.
When I was struck by how I love the fact that you track those reed canary grass removal projects, the DO before and after, and of course the impact during, and you know, that's of course that's the difficulty with the stuff, right? You got to get in and get it out of there, and while you're getting it out of there, you're, you know, scraping fish, catching them in the reed canary grass, throwing them on the bank, or stirring up muck and making the DO go to 0 and killing fish here and there. So it, I mean, for me as a restoration practitioner, we have to go to some pretty extreme measures when we're like diverting creeks and doing work and getting all the fish out of harm's way. And I've actually done that on Chimacum Creek, and it's really hard to get fish out of harm's way out there. Like, you just hide, you can't get them. And then with these downstream effects of the DO going downstream, it's like, okay, how far downstream is DFW going to make you defish because you're going to send the plume of poorly oxygenated water downstream? it's just it's a tough situation. And the phrase, which I don't like, is you got to break some eggs to make an omelet, went through my brain. And it's like,
That's
well,
right.
how many fish do we have to kill to save the fish? And it's a challenge with these maintenance issues, and just wanted to
Yeah.
say how much that struck me, and it's neat to have the data associated with those actions. So certainly
Yeah.
something for future
Appreciate,
conversation.
yeah,
Yeah.
appreciate you saying that, Kevin. And what you just said about the omelet, yeah, you like to save them all, but you got to look at the overall picture and um, the overall time that you're improving things for. But for the big picture, you have to look at that. And yeah, so I think it is what it is. You do the best you can. One thing regarding that sediment getting up in that column, we did see some dead fish, and it did clear up fairly fast downstream from there. And when you clear a reach, you're not doing the whole basin of Chimacum Creek. You're not doing you're doing like a short piece of it. And I guess that's one thing to consider when you are doing it. Better to do several short pieces on different days than great big long reaches. I guess that's one thing you could do to minimize the impact. But yeah, you're gonna have
Another thought
some
is, yeah, you're gonna have some mortality. Another thought just on that. Can you limit effects of downstream DO drop by, sometimes you put in a filter fabric into the creek that all the water runs through. When you're going to stir up sediment, it's the only thing you can do. You put I can't remember the name of it off the top of my head, but basically it's a net that catches all the silt. Would that decrease the length of the downstream oxygen diminishment, or would it still diminish even if the sediment wasn't there?
Well, what I'm thinking, Kevin, just in my mind, that anything you're going to try to catch sediment, that net's going to be plugged up before you know
It's going
it.
to plug quick.
It's not going to work. That's
Yeah.
my estimate. Yeah.
Yeah.
Well, one other thing too, looking at the big picture and any harm that you're doing, chum are downstream. They're out of the picture, really. Dissolved oxygen has improved, but way before it reaches the chum. And in the coho, when those adults are coming back, that's like November. Dissolved oxygen has improved by then. It's not a problem. So, yeah, it's maybe not as bad as it looks. And
It's almost like you need to be raking outside of the fish window then. Maybe we need to be raking in the winter when DO's better. But there's fish in the
well,
creek, right?
that's DO is definitely better there. Yeah, I mean, yeah, there's sometimes we look at things like with a spotlight. If you're just looking at one factor, like if you're looking at temperature, you say, oh well, the answer is provide shade on the creek, so we plant trees. If you're not thinking about beaver, you need to think about everything when you're improving it. And I look at some of these reaches like Ovenel, the problem that the beaver are causing, it's just pushing the water through all the canary grass. And I just wonder if things weren't better not to have planted the trees and just clean out the canary grass, every 3 years or whatever, than what we have there right now. And I think it's at the point right now where you can't even, if you wanted to, go back in time, you couldn't even get an excavator there to clean it out. You got flooded water, and anyway, we should learn from experience. And again, think about like all of the factors, not just zero in on, temperature, plant trees. That's the answer. Need to look at everything. And those beaver are definitely a factor we need to take into consideration.
Mm-hmm.
Yeah, it seems
Gary,
like,
do you think there's a way? Just sorry. Go ahead, Bob.
I'm just, anecdotally looking, like I don't know exactly when Roger had been actively dredging. I know most of it was, in the early 2000s and before, and the fish numbers were better. And so just looking at just that kind of points to, having a clearer stream that did do better for the fish. And I know there's a lot of other complicating factors related to that. And you kind of touched on that a little bit, Glenn, but I don't know if you could expand on that.
Roger has told me that, when his fields are flooded and the fish are coming back in November, that the fish, instead of being in the channel, they're out there in the field. And I think they're a lot more susceptible to not making it to the spawning ground, traveling through the field and in the channel. So, yeah. There's other things to consider.
Yeah.
And it's sometimes hard to just think of everything. And, there's this expression I've learned, and I think it goes along with a lot of things in life, things we see happening. It relates to, the work we're doing too, but it's unintended consequences. Like planting trees, the bumper sticker says habitat is the key to wildlife, and, make the habitat and they will come. And the beaver sure came. And they're nice, and then it's all like, what are you really gaining? If you're a beaver biologist, you'd say that's great. If you're a trumpeter swan person, you'd say, well, flooded fields, that's wonderful. They're having a great time out there. So, and it's not always one size fits all, like this is good. I hear the expression for fish and wildlife. Well, just taking it somewhere else, deer, they like clear cuts. They've got browse, but squirrels would rather have the trees. So it's not a one thing fits all.
Well, this definitely has me thinking about the drainage district conversations and just really curious about obviously where that's going to go and whether that's going to be reinstated. And if it is, then I think all this data would be really useful, especially like that conversation that Kevin was bringing up of like when if they do management like this where they continue to take out reed canary grass, then what days are you doing it on and over what time period and things like that. So hopefully your data collection will impact management. Glenn.
Well, my job's collecting the data and other people can decide what to do with it. I've often said that a lot of this stuff, it's not really a biological answer, it's a policy answer. Like, which would you rather have, salmon or trumpeter swans, or farmers being able to plant more crops? That's another factor. If you got, ponds out there the year round, you can't grow as much. And I'll tell you something I think about. We're living here on the Olympic Peninsula, and I'd like to see those vegetable farms going in, because we're all waiting for the big earthquake someday. Who knows? But I think the more food we can grow out on this peninsula, the better.
Yeah, I'm kind of I'm with Owen. Can't we have it all?
Yeah.
Patches of everything.
Maybe compromise helps too.
Mm-hmm. Thanks, Glenn. Alicia, are you working on oh, we have another Zoom link. We're gonna end this meeting because Joe has a really great follow-up to talk about where we are with Chimacum, and I don't want to cut him short.
Oh, great.
So we're gonna jump over to the Alicia's Zoom meeting, and I'll figure out what's wrong with my Zoom. All right, see you guys over there.
It's in the chat, so be sure to grab that link.
Yeah, I'll keep this meeting running.
Okay.
Owen, are you able to move over to that other Zoom meeting?
Not until I can't until we close this one.
Oh, okay. I'll
I can't do two at once.
oh, okay. I'm gonna move over. Do you have the link open though? I'll save the link in case you need it. I'll email it to you.
Okay.